Alrighty, so we're at 8.4. Here's your little do now. I'm gonna go ahead and go over it real quick before you guys start working on it. This is called the two-field problem. Ella Mental has 600 feet of fencing to enclose two fields. One is to be a rectangle twice as long as it is wide. The other is to be a square. The square field must contain at least 100 feet square. The rectangle one must contain at least 800 feet squared. If x is the width of the rectangular field, what is the domain of x? Plot the graph of the total area contained with the two fields as a function of x. What is the greatest area that can be contained in the two fields? Justify your answer. Alrighty, at this point go ahead and pause the video and give it a try. Alrighty, so here are my equations so far. Don't worry, it looks bad, but it really isn't, because we're going to be using this information right here twice as long as it is wide. That's going to be very important to us. But let me just go ahead and go over it. I just wrote down everything that the problem pretty much gave me. For one, I used the how much fencing we got, and I used the circumference equations. Perimeter equations for a square, which is 4 times z, and for a rectangle, which is 2 times x and 2 times y. That highlighting is a horrible choice. I was going to use blue. Anyways, so we used the 600. We got the 600. Can I get the z back? Yeah. Good. We got the 600. That should equal 2 times x plus 2 times y. That's for the rectangle. That's the pyramid for the rectangle. Plus 4 times z, which is the pyramid of the square. Then I also wrote down the limitations that are given to me, meaning the square has to be at least 100 and the rectangle has to be at least 800 feet squared. The area would be z squared plus xy, which is the area for the square plus the area for the rectangle. At this point, we have a big problem, because the idea is that I'm going to be able to take this equation, plug into that one, only have one variable. But as you know, 1, 2, 3 variables and 2 equations, you can only eliminate one variable, really. But now we're going to be taking advantage of the twice as long as it is wide for the rectangle. So give me a second. Let me go ahead and do that real quick for you. Alrighty, I made the equation look a little bit better, because now it's doable. You're just trying to choose the right highlight. Yeah, black's good. So 2x plus 4x plus 4z will be the equation for the perimeter, and the area will be z squared plus 2x squared. And the reason why I did that is because if it's twice as long as it's wide, it means that it's length equation, which I see that as a height, but if this is the width and they're talking about width and length, then this has got to be the length. If this is x, this has got to be 2x. So now I just rewrote my equations a little bit, and now I can make the equations look a lot better. So let me go ahead and do that. Alrighty, before I actually finish it up, I just wanted to talk about this step real quick. So, not sure where I just left off, but I solved for z, so I can plug it in. But because my area equation has a z squared in it, I probably want to take my z and square that anyway, so I can just straight substitute it. And when I square the top, and let me go ahead and highlight it. So when you square the top, it's going to be this squared and this squared, which is what I have right here. These two numbers squared. But that's going to be middle term, which is going to be this number times 2. 6 times 6 is 36, times 2 is 72. And then I just attached the 2 zeros, and I put an x right there. So that's why it's that number. Now I have my z squared. Now I can plug in, and then I can look forward to doing like derivatives and stuff. So let me go ahead and do that. Alrighty, I actually did a lot of talking, realized I wasn't recording, so I'm just going to say everything again. Hopefully I'm going to hit the same points. Okay, so I'm trying to get this variable by itself, not by itself. I tried to get the area equation with only one variable. So I got my z squared. I just copy and pasted it because I'm lazy. I actually had a funnier joke before, but that's just the truth. And then I took my 2x squared, and I turned it into 32x squared over 16, because I like common denominators, so I can add like terms. And I'm going to now do that. Alrighty. I combined these two things and made sure to have the 16s individually because I'm about to take a derivative and it will be a lot easier that way. For one, this bad boy, gone. Alrighty, so let's take the derivative real quick. Alrighty, so did this, found the derivative, made it look all nice and pretty, made it equal to 0, and then solve for x, and that's my x right there, whatever that is. Now this value is going to represent the maximum minimum. Let's see what the problem was asking for. The problem was asking for a greatest value. Wait, that doesn't. Alrighty. This is a parabola that's facing up. We have a positive x squared. So this is going to be a minimum value. Okay, it asked for the greatest value. I'm just going to change the problem to a minimum problem. Because we already spent so much time, I can't really go back and change stuff. And we have to move on. The video is already 6 minutes. So yeah, this will give you the minimum area possible. Let's move on. For the interest of time, the remaining of this video is going to be a lot shorter. To find the area of a plane region, you pretty much do, to find the area of anything, you do an integral. But if you're trying to find out a region within two functions, you pretty much just do this, the subtraction of those two functions. You subtract them. Because if you were to, let's say, do this area, then you would get all of this. And then if you do for the parabola, you get all of this. And then the intersecting one, when you subtract the two, would be, actually sorry, I'll be doing it from A to B. So let's say this is A. Let me just erase all that good stuff. Let me make a hard line so we know the limitations. This is A, this is B. And by the way, you always want to have your A and B to be the parts where they intersect. But now, for the first one would give you like, the F function would give you this, and then the G function will probably give you like this right here. So when you subtract the two, you're left with the region in between, because this is taken away. So like all this good stuff is gone when you subtract the two. Alrighty, so that's that. Alrighty, so let's say you have a situation like this where it's right at the x-axis. In order to get this bottom graph to become positive, because if you take its derivative, it's going to be negative, just attach a negative, so the negatives cancel, make it positive. Because if you were to do this normally, then these two areas would cancel each other out. So in order to turn this bottom area into a positive, you just attach a negative. Here's what I mean. Your integral for this integral is going to be positive because it's above the x-axis. This integral will give you negative because it's underneath the x-axis. But because you're looking for area, it's beneficial for us to make this positive, which is why there's a negative right there. All right, let's move on. All right, here's an example. Alrighty. Find algebraically, by fundamental theorem of calculus, the area of a triangular region in quadrant 1 that is bounded by the graph Bloom. The fact that it tells you that it's quadrant 1 is kind of important because it kind of gives you some limitations. It didn't tell you, but you're going to have to make sure that it's above x equals 0 and it's above the y-axis. So you have like x's. Oops, let me just do that. You know that x has to be greater than 0 and y has to be greater than 0. So you're kind of bounded by these two things. Alrighty, so if you want to know when they intersect, did they ever do this calculation? I don't see them do it. So how do they know? How do they know it starts at 1? They're starting from 0 and they're going to 1. That's what I'm seeing. So find algebraically the area of the triangular region in quadrant 1 that is bounded by the graph. Alright, well, the first thing they have to do is, the graph gives it to them. So this must have come with the example. So this example came with the graph. All right, so let's look at the graph. Let's see, they're bounded, right? So we're looking for this area right here. So I would say that if you went from 0 to, you're gonna go from 0 to 2 though. Top minus bottom. Top minus bottom. Okay. That's gonna give you 4 minus 4x. Alrighty. So just did one integral from 0 to 1. But that's not what's bounded though. Right? I mean, am I not seeing the graph correctly? Unless they're just thinking that it's symmetric, and therefore if you do half the graph, and then you just multiply by 2, you get the answer. Alright, find algebraically the area of the triangular region in quadrant 1 that is bounded by the graph. No. Okay. Yeah, I see symmetry. So there's good reason to say that if you start from 0, you can go, say, if you start from 0 and go to 1, you can get your integral, and then whatever you get, you just multiply it by 2. But I don't see them do that. But that's pretty much what I'm going to do. So from 0 to 1, the top is this bad boy. So we're going to have this on the top. This is the bottom one. This is going to be, oh, I'm sorry. Here's my mistake. I kept thinking that this is the bounded region when it wasn't. It's this. This is the bounded region. Well, when they say triangle, I immediately saw this as a triangle. But I was wrong, you see. It's this bad boy right here. Okay, that makes a lot more sense. That makes so much more sense. All right, so just to reiterate, our region is right here. Right here. This is what we're looking for. And that makes things a lot clearer, because this is going to be your top graph, which is 4 minus x squared. That's your top. This is going to be your bottom graph, because it's underneath it. And that's happening at 4x minus x squared, but they just distributed a negative in there already. So if you distribute the negative, that becomes negative 4x. That becomes positive x squared. And then you do the integral the same way they did, and you end up getting the answer 2. This was a lot easier for you because they kind of gave you in the graph where they intersected. If they wouldn't have, you probably would have just done this, like 4 minus x squared equals, and then 4x minus x squared. And then you would have had to solve it, you know? You would have been like 4 equals 4x, and then x equals 1. Ooh, that's where they intersect. But they gave it to you graphically, so you didn't have to worry about doing that. That was it. There was actually another problem, but I'm going to keep it short. We had a big do now, which we didn't really finish, which is fine. See you guys tomorrow.